Hello, welcome to the Law of Cosines. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This is for pre-calculus. We call that Math 1508 here at UTEP. Chapter 6, Additional Topics in Trigonometry, comes to you from Larson's 10th edition pre-calculus text, and this is on the Law of Cosines. The Law of Cosines states a squared equals b squared plus c squared minus 2bc cosine a. Notice the a is squared, the angle A is what we're taking the cosine of, and everything else involves b and c. B squared equals a squared plus c squared minus 2ac cosine of b. Notice the angle of b. Notice the b squared isolated. Notice inside a and c. Similarly, c, the side, is isolated, angle C is being used, A and B in between. Now don't waste a ton of time memorizing them. Notice, they're very Pythagorean. But then this part accounts for the fact that we don't have a right angle. Okay, the isolated side matches the angle that we use. The general form stays the same no matter what we call the letters. So, a triangle has sides 8 feet for A, B equals 19 feet, and C equals 14 feet. Find the measure of all three angles. Wow. So to start, we need three angles. Pick any of the descriptions of the law of cosines and solve it for one of the angles. I used a squared equals b squared plus c squared minus 2bc cosine of a, and I subtracted b squared and then subtracted c squared. Then I divided by a minus 2bc so I could get cosine of A by itself. And that way I can use the inverse cosine to find angle A. I could do this same process for each of my three angles. Absolutely going to work, guaranteed. But there are other ways we can do it instead. So, A is 8 feet, B is 19 feet, and C is 14 feet. I'll substitute my A, B, and C, and then again B and C appropriately. On my calculator, I have, of course, going to put in a parenthesis around my numerator and a parenthesis around my denominator. My calculator is faster than I am, but it's not smarter than I am. I have to tell it, hey, this whole thing is my numerator. And then we'll divide by this entire denominator. So those parentheses are really important. This fraction gives me cosine of A equals 493 over 532. If I want to find angle A, I'll use the inverse cosine. 22.1 degrees. There I go. 22.1 degrees, smallest side, pretty small angle. We'll see if it holds up. Now, I know angle A. I want to find angle B. I could use the law of cosines again, like I mentioned, or sine of B over 19 equals sine of 22.1 over 8. I could use the law of sines because the law of sines doesn't use any squares. There's not a whole bunch of subtraction going on. I don't have to remember too many formulas. The ratio, proportional setup, quite straightforward. If I multiply both sides by 19, I isolate the sine of B. Therefore, B is the inverse sine of 19 times the sine of 22.1 degrees over 8, which gives me an answer of 63.3 degrees. So I have angle A, 22.1 degrees, angle B, 63.3 degrees, and now we can find angle C. I could use the law of cosines again. I could use the law of sines again. Or I can say, hey, why work that hard? I know all three angles have to add up to be 180, and since these are found values anyway, I might as well just go for it. Angle C is 94.6 degrees, and I have found the measure of all three of my angles. So don't get stuck in the fact that, hey, this is on law of cosines. We have to use law of cosines, have to. No, it's another tool. But don't ignore all the other tools that you have at your disposal. Let's try some word problems. The pitcher's mound on a women's softball field is 43 feet from home plate. All right, pitcher's mound, 43 feet from home plate. This is where the batter stands, for those of you not familiar with women's softball or baseball in general. The distance between the bases is 60 feet. I want to know how far is the pitcher's mound from first base. And we're taking this to be the center of the pitcher's mound from first base. So if I take apart what we're really looking at here, I have a distance of 43. I have a distance of 60. This is home plate. and this is first base. Now I am claiming that our angle here at the bottom of the triangle is 45 degrees, and here's why. The softball or baseball infield makes a diamond shape, and that diamond shape is actually a square, right? Rectangular figure, same length on all sides, which means each angle has a measure of 90 degrees. And it's a fact that the center of the pitcher's mound, the rubber, is in the middle of the plate. Therefore, it cuts this 90-degree angle directly in half, leaving us 45 degrees here on the right towards first base. All right, so we have 43 is the distance from pitcher's mound to the plate. 60 feet is the distance from home plate to first base. I want to know this distance D, and I have the angle across from it, 45 degrees. That's exactly what I need for the cosine law of cosines. I know that D squared will be 43 squared plus 60 squared minus 2 times 43 times 60 times the cosine of 45 degrees. Given this angle, I find the side across from it using the law of cosines. I let my calculator do the work. I type it in exactly like that, making sure I'm in degree mode, and I'll get D squared is 1800, more or less. And we take the square root, and the distance from the pitcher's mound to first base, nearly identical from pitcher's mound to home plate, 42.3 feet. Good to know when you're watching the World Series of softball from Oklahoma. A ship travels 60 miles due east. Then it adjusts its course northward to from point B. Wow, that's written horribly, isn't it? So a ship travels 60 miles due east to a point B, then adjusts its course northward. After traveling 80 miles northward, the ship is now 139 miles from its point of departure. So we're at sea, and it's 139 miles from its point of departure. I'm pretty sure I typed that in the weirdest way possible. So what I want to do is describe the bearing from point B to point C. So it'll be north, and then I'll rotate to the east, but how much? And that's only if my drawing is accurate. Let's see. Once we get a general sketch, we'll make a plan, knowing that our bearing will be angle B, the full angle, minus this 90 degrees. So let's find angle B first. I can find angle B, this portion, because I know I have gone 60 and then 80 and angle B in the middle, along with a 139 here. That's a 3, hard to see. So that's 139 squared minus 80 squared minus 60 squared, all over a negative 2 times 80 times a 60, and of course I used parentheses when I put this in my calculator. This gives me a value of negative 3107 over 3200. If that's what is equal to the cosine of B, then B is the inverse cosine of negative 3107 over 3200, which is a total of 166.15 degrees. So my angle's not quite steep enough. This full angle is 166.15 degrees. But I want to describe the bearing. Angle B is the full 166.15. Subtract off 90 of that. Why do I want to subtract off 90? Remember, angle B, if I put a perpendicular here, this is 90. And I really want to know north how many degrees to the east. And that's where I get my north 76.15 degrees towards the east. And subtracting that 90 degrees, I've taken off all of parts to the west. A 100-foot vertical tower is to be erected on the side of a hill that makes a 6-degree angle with the horizontal. I want to find the length of each of the 2 guy wires that will be anchored 75 feet uphill and 75 feet downhill from the base of the tower. With our sketch, we see the 100, the right guy wire, 75 feet away from the base, will be uphill. It's going to be a little shorter. Whereas the 100-foot vertical tower, the left guy wire is going to have to be a little longer because it goes downhill. And the 6 degrees, that's going to come into play because we will kind of think of this extension right here in creating our triangles. So let's do that. Let's take a look at each of these separately. On the left, 75 feet down the hill, 100-foot vertical tower. I want to find the length of the left guy wire. This is 96 degrees because remember, from vertical, it's 90, and it's adjusted at 6 degrees, so this will be a 96-degree angle. Across from the side I'm looking for, that's the angle I need. L squared equals 100 squared plus 75 squared minus 2 times 100 times 75 times the cosine of 96 degrees. Put it all in my calculator at once. You make fewer mistakes if you type less frequently in the calculator. You don't lose track of where you are. That's a fairly large number, but that's my L squared. So I take the square root, and I find that L is 131.1 feet. That's the length of wire I'll need exposed, because you need a little bit more wire to attach it, but 131.1 feet of wire. I can then take a look at the right side. 100-foot vertical tower, attached 75 feet up the hill. This other angle is 96. Remember, they make a nice straight angle, so this angle is 84. I want to find the length of R. R squared equals 100 squared plus 75 squared. That's the Pythagorean part. Minus 2 times 100 times 75 times the cosine of 84 degrees. This is the part that adjusts for the fact that it's not a right angle. Enter this in my calculator, take the square root, and I find that the right side will be 118.6 feet long, the exposed portion of the wire. Last example, I'm a sports fan. You probably could tell by the front picture on all of my videos. Seahawks fan, grew up in the Northwest. But I'm also a baseball fan. So the baseball player in center field. Here we have a baseball diamond, for those of you not all that familiar with America's pastime, baseball. We have left field, center field, and right field as the batter faces left, center, and right. So the baseball player in center field is playing approximately 330 feet from the TV camera behind home plate. 330 feet, that's where he's playing. A batter hits a fly ball, and that's a ball in the air, that goes to the wall 420 feet from the camera. So it's 420 feet from the camera to the wall. The camera turns 8 degrees in order to follow this play. What I want to know is approximately how far does the center fielder have to run in order to make the catch? Well, I have this baseball set up and some things labeled, but really I want to pull this triangle out. 330 is the distance he played. 420 is the distance the ball went to the wall. 8 degrees, the amount of rotation. How far did he run? Notice R squared across from my angle. And I have the law of cosines to tell me that R squared equals 330 squared plus 420 squared minus 2 times 330 times 420, cosine of 8 degrees. I do all of that in my calculator at one time. Find the square root. 103.9 feet. He runs 103.9 feet so quickly that he probably makes that catch look easy. Baseball. There's a lot of math in baseball, but it doesn't all have to be statistics. That's it on the law of cosines. And for now, that's my last lecture on pre-calculus. If there's anything I haven't talked about in this series that you want to know about, throw me an email, mathwithtuesday@gmail.com, or comment here on my YouTube channel, and I'll do what I can to get to you. Thank you for listening.